In this video, we're going to graph exponential functions and explore the transformations that happen with the exponential functions. So in the first two examples here, all we're doing is putting in these values in for x and then writing the answer as an ordered pair. So for f of negative 3, then this is 2 raised to the negative 3, which is the same thing as 1 over 8. So I put in negative 3 and 1/8 comes out. 2 raised to the negative 2 is 1 over 4. Put in negative 2, 1/4 comes out. 2 raised to the negative 1 is 1 over 2, so I put in negative 1 and 1/2 comes out. I put in 0, so 2 to the 0 is 1 all day long, so it is is 0 comma 1. 2 to the 1 is 2, so that is 1 comma 2. 2 squared is 4, so that is the point 2 comma 4. And then 2 to the third is 8, so that is 2 comma 8. Now, if we're asked to graph these, I'm going to go over here to the XY plane. Let me see if I can do this as a line. Nice line here. There's my x-axis, and here's a nice line here. Here is my y-axis. I couldn't match that line. Well, that's unfortunate. Anyways, so we have this y-axis right here. Now, if I go to put in these ordered pairs, this one's pretty easy because I know where that is. I put in 1 and 2 comes out. I put in 3 and 8 comes out, so it's way up here. And then, of course, when I go on this side, 1/2, and then it just gets smaller and smaller. So this is what the graph looks like by connecting all those points of f of x is equal to 2 to the x. Now, if we take a look at b, we're going to do the same kind of thing, but now it's going to be 2 raised to the negative 3. So in other words, it's 2 to the third. So this is negative 3 and 8 comes out. 2 raised to the negative 2. Negative 2 comes in. 4 comes out. 2 to the negative 1. Negative 1. Negative 1 gives me negative 1 comma 2. And of course, 2 to the 0 is still 1. And so 0 and 1, and then I'm going to continue. Now I have 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and you can see that this is negative 1 and 1/2, negative 2 and 1/4, and negative 3 and 1/8, positive 1/8. So now, close that and close that. What we're going to get is, let me go ahead and put my axes here. It's my y or my x-axis, and now I'm going to do my y-axis. There. See, it did the shape that time. Okay. When I graph these, I'm going to graph the easy ones first, and so I have the 0, 1, negative 1, 2, and then negative 2, 4, 1, 2, 3, 4, and etc. Oh, I'm kind of missing some of these points. I kind of skipped some points up here. Oh, well, we're all good. Anyways, this is going to look like this. Okay. This is f of x is equal to negative 2 raised to the negative x. And if I knew what the graph of 2 raised to the x is, then clearly I would know how to get the graph of 2 raised to the negative x through transformations of the graph. Let's continue on. So let's continue on, and we want to do this. We want to make sure that we don't rotate weird. Okay, so moving on. Oh, and for some reason, that line wanted to come with me, and I don't know why. So let me see if I can just move this over there. Okay, I'm just going to move that over there. All right. So what I know is that if I have a function that looks like this, f of x is raised to the 2 raised to the negative x, this can be the same thing as 1 over 2 to the positive x using my rules of exponents, which is the same thing as 1/2 raised to the x. So if my base is obviously greater than 0, but less than 1, then I know that it is decreasing from left to right on my domain. All the transformations are going to be maintained, so let's talk about what we expect to look like. Every single one of these in which I have an a value here is always there, where a is equal to 1, so I'm not worried about any kind of transformation. Will always have these properties. It'll be 1 to 1. It'll have a horizontal asymptote at y equals 0. The domain will be negative infinity to infinity. The range, because of this horizontal asymptote, will be 0, non-inclusive, all the way up to infinity. I do not have any x-intercepts. I do have a y-intercept, and if my base is bigger than 1, then it will be increasing, and if my base is less than 1, it will be decreasing. So let's take a look at an example in which we have some transformations. Now, the function, when I'm talking about inside and outside, is going to be up in the exponent. So what I have is my g of x. If my f of x is equal to a b to the x, then my g of x, actually, you know what? I'll do it this way. I'll just start out with b to the x. Then my g of x is going to be equal to a b to the big B, x minus c. This should look really familiar, plus d. Now, every single transformation we learned at the beginning of this quarter is still true. My a is a vertical shrink stretch reflection across the x-axis. My b is a horizontal shrink stretch reflection across the y-axis. My c is a horizontal movement left or right, and my d value is still up and down. So notice that this plus 3 means that I take my original function 2 to the x and bring it up 3. If it is a minus 3, then I bring it down 3. And what's happening is that ordered pair right here, all of them are going to go through this ordered pair 0, 1 unless there's a transformation. All of them will have this line y is equal to 0 as the horizontal asymptote. Because I went up 3, it switched to y equals 3, and this point went up 3. If I go down 3, then my point goes down 3, and my horizontal asymptote also goes down 3. With the translations, notice that I have a plus 3. That means this point is going to go back 3 to right here. And if I have a minus 3 at this point, goes to the right 3, and it goes to right here. The shape does not change. It's just moving left to right. Because of the fact that I have the x plus 3 and x minus 3 in the exponent, I'm not moving up or down. I'm moving left and right. It is a horizontal movement, not a left and right movement. Now, whenever I have this a value out front that does exactly what we expect, it's going to stretch it in the vertical direction. Notice how that I still have the same horizontal asymptote, but instead of going through this point, it's going to be moved up as a multiplier by 3. So I took the ordered pair 0, 1 and multiplied it by 3, which gave me the 0, 3. Similarly, here's my original point, which is again 0, 1. This 1/3 is going to go ahead and multiply my x value, my y value by 3, which tells me that my point now is 0 and 1/3. My horizontal asymptote did not change. And then, of course, we can combine we can also do the horizontal shrink and stretch. So the horizontal stretch is when my b value, the big B value, is greater than 0, because remember this is inside the function. So since b is 1/3, that tells me it is 3, stretched in the horizontal direction by a factor of 3. So it's a 3, it's going to be 3 times as wide in the horizontal direction. So 3 times as wide in the horizontal direction. Just like here, do this in red, just like here, my b value is 3, which means I am 1/3 as wide in the horizontal direction. Okay? And of course we have the reflections. Notice that the negative in front reflects it about the x-axis. The negative on the exponent reflects it about the y-axis. So here's kind of a wrap-up of what it looks like in terms of the parent function, where I have c is going to go left or right, d is going to go up or down. If my coefficient is absolute value is greater than 1, it's a stretch. If the absolute value is less than 1, it is a shrink in the vertical direction. And the compressions in terms of the horizontal is always the reciprocal. The reflection happens when I have a negative out front of my b about the x-axis, and a reflection about the y-axis means my exponent is negative. The general translation is AB raised to the big B, B being your horizontal shrink or stretch, and C being your left and right, and D being your movement up or down. So if I'm asked to find the equation or describe what the transformation is before I label my points, then I know that this is going to move all of my points because it's in the numerator. It's going to take all of my points and it's going to move them left. So if I know my left and my right, it's going to move them left one value. Okay? So when I go to put in -3, I'm really doing 2 raised to the -2, which means that this is the ordered pair -3, comma, and this would have been 1/4, positive 1/4. And so when I go to draw mine, if I know my basic points for this squared, so there's my x-axis, here is my y-axis, that each one of my points, which would have been here and up here at 4, and then this one, are all going to be moved with this transformation back one. So this is going to go here, then here, then here, and then here. So this is my new graph with a transformation where I picked everything up and gone left 1. So my point, which would have been at 0, 1, transforms into -1, 1, because I've gone back 1, I've gone left 1. Okay, let's talk about the transformations here. So this negative is going to reflect over the x-axis, and then I'm going to go up 1. So again, I'm going to draw my x-axis, and I'm going to draw my y-axis. The fact that I am going to reflect across the x-axis, it would then be, so my original points are this one, and this one, and then of course this one. So this is my original function. To reflect it across the y-axis or x-axis, it's going to be this one, and this one, and this. So that's the reflection part. Now what I want to do is I want to move it up 1. So then this would be my final graph. So I'm going to do this. I'm going to erase this red because that's just kind of giving me my intermediate step. And then my final answer looks like this. It goes through this point, and this point. And so that's what my final graph looks like. Again, I can do this point by point. Now let's talk about what everything happens here. So this is a vertical stretch by 3. I'm going to go left 1, and I'm going to go up 1. All right. So let's go ahead and put in my axes. So here, actually, you know what? I'm going to do this. I'm going to move it down because then I'm going to have to go up 1. So I'm going to just move the axes down here just so that I can see those points. So there's that one. And then, of course, I'm going to put my x-axis in there, or my y-axis in there. So I know that it's going to go up 1. Typically, I will do this last, but I do know it's going to go up 1. So I'm just going to put that there. Y is equal to 1. Now all of my points are going to go left 1 so that when I look at my ordered pairs, that this point right here, the point 0, 1 is going to go to negative 1, 1. And then it's going to be stretched by a factor of 3 on the y value. So then this is going to go to negative 1, 3. So that's where that new point is going to go to. So negative 1, 3. 1, 2, 3. The other point that I would have had is the point, this point right here, which would have been the point, excuse me, this would have been, let me make sure I can count right, because clearly I can't always. So negative 1, 1, 2, 3, negative 1, 3. So that's that point. Okay, the other point I would have had would have been the point 1, 2. So I know that that's going to go left, so that's going to go to 0, 2, and then I'm going to multiply it by 3, so that means I have 0, 6. So 4, 5, 6. So it's going to go there. Now I would continue to do this point by point, and so that's what my graph is going to look like. Okay, so in this part, we're going to match the graphs, and we're going to use the information that we know in terms of our coefficients out front and by looking at the bases. So let's start with the 4 as the multiplier up front, the vertical stretch. What that the a b to the x does, if I don't have any movement left or right, so horizontal shifting left or right or vertical shifting up or down, then this vertical stretch is going to tell me where I'm going to cross the x-axis. And these are the only two equations in which I have a 4. So I know that this must be 4. It's the only one I have that must be 4. And then it's a matter of looking at the base. Now we know if the base is greater than 1, then we're increasing. And if the base is less than 1 but greater than 0, we are decreasing. So combining those two, since this base for D is greater than 1, then that must be that D. Similarly, this must be B. So where we are right now, based on the fact that my graph is increasing from left to right, and it has an intercept of 4, at least that's our guess, that's going to be 4, then this equation right here is 4, 1 plus 2, 4 times 1.2 raised to the x. That's that function. And that means this c must be f of x is equal to 4, 0.69 raised to the x. Now those were the easy ones, so those are done. Now it's a matter of looking at these other ones. So I know that E, C, B, and A must be these here. And what I'm going to do then is look for the ones that have bases that are bigger than 1, right? So I'm going to look for the bases that are bigger than 1. That's this one, and that's that one. So those are the two that have bases bigger than 1, and that coefficient multiplier out front is 2. So we know this is more than likely the point 0, 2, just like this is more than likely the point 0, 4. So then I'm trying to decide which one have my bases bigger than 1. So either this is E or it's F, or this is E or it's F. So what we do is we look at the base itself. The bigger the base, the closer it's going to approach the y-axis, the quicker it approaches the y-axis looking. So the steeper it is, the bigger the base. So we have to decide which one of these is the steeper number. That one or that one, which is the larger number. So since this is the larger number, we know that E must actually be E. So this is f of x is equal to 1.59 raised to the x. That means this must be the f of x is equal to the 1.28 raised to the x, and don't forget that 2 up front. So now we're done with these two. Now I have to figure out which one of these. So when my base is less than 1 but greater than 0, then I know I'm decreasing. So I know that this is either A or B, and this one is either A or B. So I have to decide which one is which. And we go back to the way that we think about which one do we expect to decrease? Do we expect it to decrease slower, or do we expect it to decrease faster based on going from left to right? Now, if you're not certain, think of the fact that if you take 0.69 and the reciprocal of that, so that is 69 over 100, and the reciprocal of that would be 100 over 69. Similarly, the 0.81 raised to the negative 1 would be 81 over 100, which the reciprocal of that is going to be 100 divided by 81. Now this is f of negative 1. Still have a 2 out front. F of negative 1, still have a 2 out front, still have a 2 out front, 2, 2, and 2. So we ask ourselves, if I were to put in negative 1, so right about here is negative 1, which one of these is going to be the bigger number? Is it 100 divided by 69? Or is it going to be 100 divided by 81? Well, clearly 100 divided by 61 is going to be larger than 100 divided by 81. That means that this b value must be f of x is equal to 2, 0.69, mathing today, mathing. So 0.69 raised to the x must be that one. That means this lower one, a, must be 2, 0.81 raised to the x. Okay? So that's how I matched them, is I started out with my coefficient multiplier, that a value, if you will, and that's going to tell me where I'm going to cross if I don't have a vertical or horizontal translation, left, right, up, or down. So this is going to tell me where I'm going to cross. These were the only two. So D and F are the only two that could have crossed up here, and all the rest would have had it crossed somewhere here. I know that there is not any grid marks, so you have to think through this logically. Obviously, this is a larger number than this one on the y-axis, and then it's a matter of looking at the bases. The larger the base, the quicker it increases as you are going from left to right. So obviously this one has a bigger base than this one. And the smaller the base, the quicker you need to decrease, whereas this one had a larger base, so it wasn't decreasing as quickly. So now we're going to look at, if I have the a, b raised to the x of all of these graphs, I'm trying to determine which one of all of these graphs is likely to have the largest b value. So I'm looking for the base. Which one is going to have the largest base? So for this, my largest base must be this one because it is increasing the fastest. So this is the b with the largest base. And then I look to see which one of these is decreasing the quickest. Which one of these is decreasing the quickest? So this one, if I look at C, it seems to be decreasing not too bad. But if I look at B, it's not quite decreasing at the same rate. That C seems to be decreasing the quickest. So then C must be the one where my base is my smallest base. And again, that's because if you think about it, if you had a base of 0.2 and you have a base of 0.1, 0.1 reciprocal is going to be a larger number than the reciprocal of 0.2. Then we have to figure out which one of these has the largest a value. Well, I'm going to look just strictly at my steepest line, and I don't care, or the steepest curve, I should say, it's not a line, the steepest curve, and I don't really care about whether or not it's increasing or decreasing. I'm looking for the steepest line. And so the steepest line happens to be the one that has the smallest base. So A is the largest because it has the steepest incline and also has the highest y-intercept, because we are not moving left to right, up to down. We are just doing that vertical shrink or stretch. So then I'm trying to decide which of these has the smallest value for A. So I'm going to look strictly at the y-intercept. The one that has the smallest y-intercept is that one. So F must have the smallest value for A. And all I did was look at the multiplier in front. All right, so that's it for this video.